Okay, hello everyone. In the previous lecture, we started learning about the gray box testing methods, including fuzzing method, which are mutation-based fuzzing and generation-based fuzzing. So in this lecture, we will continuously learn about the mutation-based fuzzings. And as I mentioned before, these mutation-based fuzzing techniques are really practical, and these techniques are usually published more in the secret field than in the software engineering field. Anyway, let's start with this week's lectures. So in today's lectures, I will introduce a recent trend in the mutation-based fuzzings. At a high level, the previous techniques in mutation-based fuzzing can be seen as program agnostic approaches. And recently, program adaptive techniques, which observe the behavior of the target program to learn the optimal strategies, have become a trending approach to achieve better performance in this fuzzing field. Okay, before introducing these trending approaches, I will start by reviewing the mutation-based fuzzers. As we learned in the previous lecture, AFL is the most representative mutation-based fuzzers. And the very first step for using AFL fuzzer is conducting the lightweight instrumentations. And the goal of this instrumentation is to track the coverage information of the program execution with each test case or mutant. So AFL takes the source code as input and returns a binary that is able to track the coverage information. That is, AFL is to use this compiled binary for generating test case. And actually, in AFL, the coverage coverage information denotes the path transition informations. And this path transition is the transition between basic blocks. So for example, considering this following while loop, which consists of 3 basic blocks. In this while loop, the transition from A to B is different from the transition from B to A. And please note that this default version of AFL uses the path transition as coverage information to guide fuzzer effectively, but it can use other type of coverage information such as branch coverage as well. And after instrumentations, AFL takes the well-structured seed and the compiled binary as input, and then iteratively select a seed from the seed pool and mutate the selected seed based on the predefined mutation strategy until the budget expires. Then as a final output, it returns a number of generated mutant, more precisely, interesting generated mutant and bound box. And as we learned before, the interesting mutant denotes the mutants that succeed into finding new bugs or executing new paths. And at the end of the previous lectures, I said that there exists 2 critical components in the mutation-based fuzzing, which are seed selection strategy and seed mutation strategies. The former strategy is about selecting the seed first among the seed pools. And on the latter strategy determines how to mutate these seeds. And let's look at the recent researches for presenting these 2 strategies. The recent mutation-based fuzzing is changing from the program-agnostic fuzzing to program-adaptive fuzzings. These terms, such as agnostic and adaptive itself, describes the recent trend. the program agnostic fudging techniques such as AFL are to use a fixed seed mutation or seed selection strategy regardless of the target programs. That is, the criteria for selecting or mutating the seed during the testing does not change at all. And on the other hand, program adaptive fudging techniques such as MOPT are to employ the adaptive seed mutation or selection strategy, which is changed for each target programs. So for example, the job of the mutation strategy determines how to mutate the seed. And in this context, this program agnostic strategy is to generate the mutant in the same way when testing the program A or testing program B or testing program J. And so this agnostic strategy does not reflect the characteristics of the target program during the testing. More specifically, in general, this program agnostic mutation strategy refers to the strategy that determines how to mutate the seed at the havoc stage rather than deterministic stages. And in AFL, the uniform distribution of selecting mutation operators such as 1-bit flip or 2-byte flip corresponds to the program agnostic strategies. So this uniform distribution is conforms the program agnostic strategy. Therefore, the program adaptive strategy aims to adaptively change the seed mutation strategy depending on the target programs. So, for example, when testing program A, the mutation strategy is changed to as seed mutation strategy A. And when testing the program B, this strategy is adaptively changed as the mutation strategy B, thereby reflecting each characteristic of the target program and maximizing the performance of fudgings. So this is the program adaptive seed mutation strategy. And I will introduce one of the program adaptive mutation strategy called MOPT, which has been published in the Eugenics Security 2019. And the motivation that the effective mutation operators are different from each target program, which is clearly demonstrated as these below figures. In the leftmost table, each color indicates the type of each operators. For example, the purple represents a 1-bit flip operator and green represents a 4-byte flip operators. And this pie chart shows the percentage of interesting mutants generated by each mutation operators. So that is having more percentages means that this operator is more effective for finding or generating interesting inputs. And as you can see, when testing the open source program, namely AVComp, the 1-bit flip operator contributed the most to generating interesting mutant as of 49%. So what about testing other programs? As you can see, when testing another open source program, EXIV2, the most effective mutation operator is 1-byte arithmetic increasing operator as 28%. That is, if you look at the two pie chart at the same time, we can see that the percentage of the arithmetic increase operator highlighted in green when testing EXIV2 is more than twice that of the same operator when testing AVComps, which implies that frequently choosing a different operator for each target program can maximize the performance of fudgings. This is the motivation of MOPT. And in fact, all of the program adaptive fudging techniques usually share the same motivation as the one of the MOPTs. So as you expected, the goal of MOPT is to find the seed mutation strategy optimized for the target programs. In particular, this technique focused on designing an adaptive strategy in havoc stage, which is having a lot of randomness for generating mutants. More specifically, in havoc stage, this technique MOPT aimed to find an optimal distribution of selecting these mutation operators during testing. So like this figure, this adaptive technique does not rely on the uniform distribution, but to assign the different probability to each operators. For example, when testing the program A, MOPT will assign 55 sampling probability to 1-bit flip and the 10% probability to 2-byte flip, and so on. And this program adaptive strategy will assign the different sampling probabilities for mutation operators when testing another program B. And to achieve this goal, that is to adaptively change the probability distribution of the mutation operators, the key idea of MOPT is to employ an online learning algorithms. More specifically, they have present a customized particle swarm optimization algorithms, which is also known as PSO algorithms. Actually, their customized learning algorithm is different from the typical particle swarm optimization, but sharing some notion or intuition of the original ones. Anyway, let's clarify the terms such as swarm and particle used in these customized PSO algorithms. In this work, the particle denotes a single probability of sampling a single operators. For example, the sampling probability of 1-bit flip operator, such as 24%, corresponds to a single particles. And a single swarm is a probabilistic distribution of selecting mutation operators. So intuitively, a swarm can be seen as a set of particles. And using these particle and swarms, I will explain how to find an optimal mutation strategy of the target programs. The first step is to initialize multiple swarms. In implementation level, MOPT heuristically determine the number of swarms as 5. At the initial stage of the learning phase, as there is no prior or accumulated learning data, the probabilistic distribution of each swarm is initialized as a randomly generated distribution like these figures. For example, the probability of 1-bit flip operator in the first swarm is initialized as 24%, while the probability of the 1-bit flip in the last swarm is initialized as 21% as well. That is, the probability of each operator in each swarm is different, as you can see. And then this learning algorithm is to simply generate many mutants by sampling from each swarms respectively. And this is also a detail. This technique generates about 10,000 mutant based on each swarms. And that is, it will generate 50,000 mutant in total during these single iterations. And at a high level, with all these generated mutants, this learning algorithm will update each probability of mutation operator in each swarm respectively. More specifically, it updates K swarms, 5 swarms based on the 2 kinds of efficiency, which is local and global efficiencies. And by calculating these efficiencies, each particle, which is each probability of mutation operator, will be updated accordingly. And for example, as you can see, the probability of 1 bit flip in the first swarm will be increased, and while decreasing the probability of 1 byte flip as well.